Hello friends, I'm Urvashi, an educator on Unacademy. You can follow me on Unacademy Learning app where you can find many other courses as well. In this lesson, I'm going to explain generation and demodulation of SSBSC, that is single sideband suppressed carrier. Please rate, review and recommend this lesson among your friends and also subscribe to our YouTube channel, Unacademy Engineering Students. So let's start the lesson. Have a good day. Welcome to the course Communication System. In our previous lecture, we have discussed with SSBSC, that is single sideband suppressed carrier, and in this lecture I am discussing how to generate this SSBSC signal and how to demodulate it. For the generation of this SSBSC, we have the method known as the frequency discrimination method or the filter method. In this method, SSBSC is generated by passing it through a band pass filter, and hence it is known as the filter method because we are using here the band pass filter. This is the block diagram of this SSBSC generator. In this, a product modulator and a band pass filter is present and a carrier signal is generated through the local oscillator. And when this message signal and carrier signal get multiplied by this product modulator, then we will get the DSBSC signal. That is, first we have to generate the DSBSC signal, and then on passing that signal by the band pass filter, we will get the SSBSC signal. So first we will see the spectrum of the DSBSC, and on passing it with band pass filter, we will get the spectrum of this SSBSC. Let us consider a message signal MT whose spectrum is this MF, and this is the spectrum of this DSBSC signal, in which no carrier is present but both the sidebands are present. If we have a band pass filter in the range FC to FC plus omega, then we will get the upper sideband in the output. Then that time SSBSC contain the upper sideband. And if we have the band pass filter ranging from FC minus omega to FC, then that time in the SSBSC spectrum we will get the lower sideband. And here I am using the band pass filter with the FC to FC plus omega, so here we will get the upper sideband. On multiplying this DSBSC signal with the band pass filter, then we will get this SSBSC signal, which contains the upper sidebands. But what is the disadvantage of this method? Disadvantage is that it is not possible to have the ideal band pass filter. That is, sharp edges at the band pass filter is not possible practically. And in the output of this SSBSC, we will have some of the part of this lower sideband along with the upper sideband. Or in the lower sideband case, we will have some upper sideband part. So it is not possible to recover the message signal from this because here the symmetry property get disturbed. So how we will get this message signal in the output? Due to this unwanted portion, we can't recover this message signal. So in this way, practically the SSBSC fails here, and it can only be used for the voice transmission but can't be used for the audio and video transmission. Now let us see how to demodulate this SSBSC signal. For the demodulation of SSBSC, we have a method known as the Synchronous Detector method, which we have also used for the DSBSC and the AM. This is the block diagram of this synchronous detector, in which a multiplier and low pass filter is present. On applying the SSBSC signal and this carrier signal at the input of this multiplier and passing that signal with this low pass filter, we will get our message signal back, that is our message signal MT. This is the equation of the SSBSC signal, that is AC MT by 2 cos 2 pi FCT minus plus AC M cap T by 2 sin 2 pi FCT. And what is this M cap T? It is the Hilbert transform of the MT. Let us assume that the local oscillator output is AC cos 2 pi FCT, that is the perfect synchronization case. and the output of the multiplier will be SSBT into local oscillator output. That is, the multiplier multiply this signal and this carrier signal. And at the output of the low pass filter, we will get AC square MT by 4, as it only allow the lower frequencies but reject the other frequencies, and we can recover our message signal back from this, as the amplifier amplify it, and in the amplifier the blocking capacitor block the DC component, and we will get the message signal in the output. Now let us take the second case of the phase shift, that is the no phase synchronization case, in which the local oscillator output is AC cos 2 pi FCT plus phi, and the output of the multiplier AC MT by 2 cos 2 pi FCT minus plus AC M cap T by 2 sin 2 pi FCT into AC cos 2 pi FCT plus phi is present, and the low pass filter output is AC square MT by 4 cos phi plus minus AC square M cap T by 4 sin phi. Earlier in DSPSC we will getting this component only, but here this extra component is also present, and when this value of the phi is 0, that time the output is AC square MT by 4, and from this we can recover the message signal, and when phi is 90 degree, that time the output is AC square M cap T by 4, which is not equal to 0, while in the case of the DSPSC it was 0, and also in the AM it was 0. So there were the problem of the QNE. What is QNE? QNE is quadrature null effect, but it is not present in SSBSC because of this M cap T, which is the Hilbert transform of the MT, and from this we can recover the message signal band. So in the SSB demodulation, no QNE is present, that is, it is not affected by the QNE. Now what are the advantage of this SSB? First advantage is that here in SSB power is saved, because in this the carrier is suppressed, and next is the bandwidth is saved. How bandwidth is saved? Because in this SSBSC we are having only the one sideband, that is one sideband also gets suppressed, so bandwidth get reduced. So in this way we have saved the bandwidth. And another is that here no QNE is present. But this SSBSC also have some drawbacks. And what are the drawbacks? First is the demodulation is complex. As we were using the synchronous detector for the demodulation, so demodulation is complex as it requires additional circuitry for the phase synchronization purpose, and it is also limited to voice transmission only because of the impractical bandpass filter. So it can be only used for the voice transmission, but we can't use it for the audio or video transmission. So these are the drawbacks of this SSBSC, that it is limited to the voice transmission only. But in our next modulation technique we will see that how to use the technique for the audio or the video transmission. And the video transmission is the combination of the audio and the video. So both audio and video transmission will be possible through our next modulation technique, which we will see in our next lecture. So that's all about the SSBSC modulation technique. Thank you.